All right, area problems with related rates. We've already saw some of these in previous videos, but this one will just focus on area. These will be a little bit trickier because there'll be some kind of like word problems, obviously, but let's see how it goes. All right, so circle area, I'll be the judge of that. A circular puddle. All right, so right away we're thinking circles. All right, stash that away. Of oil is growing on the garage floor at 20 centimeters squared per day. What variable could that be? How fast is the radius of the puddle changing when the radius is 10 centimeters? Okay, weird. So they're asking for dr dt. They said the radius equals 10. But then the question is, what is this given? So you'll notice that so far I don't know which formula to use. I mentioned circle area up here, but if I hadn't told you that, how do we know to use area? Well, let's see. It's growing at 20 centimeters squared per day. So sometimes they're going to do this to you. You have to use the units to figure out what they're talking about. And centimeters squared is a unit of area. So they're telling us the dA dt, the rate of change of area of the puddle, is 20 centimeters squared per day. Alright, so looking at this amalgam of letters, I think that the area formula is the way to go. Because if I started with area equals pi r squared, when I take the derivative, I'll end up with a dA dt, a dr dt, and an r, which is all good stuff. I want the dr dt, and then all the other stuff I can just plug in. Alright, so let's take the derivative with respect to t. So we'll get dA dt equals, if I take the derivative, I get 2 pi r, it's a bad pi, sorry about that, times dr dt. Alright, once again, if you forget dr dt, bad news, you got the problem wrong. Of course, we wouldn't have anything to solve for either, since that's what we're solving for. So, if I want to get this by itself, I got to divide both sides by 2 pi r. So I'll get that dr dt equals dA dt over 2 pi r. So that's going to be dA dt, they told me is 20, over 2 pi and radius, 10 centimeters. Alright, so when I plug and chug that on my calculator, I got 1 over pi, because 2 times 10, that cancels that, and I get 1 over pi, which is 0.318. So not too bad. How fast the radius changing? So that's going to be, looks like there's a puddle about centimeters. And it's going to be per second or per day? Per day. That makes a lot of sense. Usually an oil spot on the garage has been forming a long time by a very slow leak. So how fast is diameter changing? Alright, so I know how fast the radius is changing. Wouldn't the diameter just be double that? Because for every centimeter it grows this way, it also grows a centimeter this way? Because it's just growing outwards. So right away I just know it'll be 2 times 0.318, which is 0.636, I believe. So that's one way to do it. The other way to do it is like, oh, so d, diameter equals 2 times radius, right? So now you just look at that. That's just a formula I can take the derivative of with respect to t. So I get that dd dt equals 2 dr dt, which is 2 times what I just got. So either you'll notice that I got the exact same thing. I just multiplied 0.318 by 2. And that'll also be centimeters per day. Alright, excellent. Not too bad. Alright, so now we've got a waffle cone. Let's see what happens. It's filling up with hot fudge. Alright, so we've got a waffle cone with a 60-degree tip. So, as usual, the devil's in the details of the drawing. So we got a waffle cone like this, and it's got a 60-degree angle here. Now whenever I see a 60-degree angle in a problem, I'm thinking it's either part of a 30, 60, 90 triangle, or if I split it in half, it'll be part of a 30, 60, 90 triangle. And I'll get a 30 right here for half of it. So keep that in mind as we progress in this problem. Alright, so the tip is being filled with hot fudge. As the fudge rises, how fast is the area of the exposed fudge growing? So they're asking for dA dt of the fudge itself, so like this little circle of fudge at the top of whatever level we're at, how fast is the area of that little circle growing? When the syrup is 5 centimeters deep, so that means I need a variable for depth. Maybe we'll call it h. When the syrup is 5 meters deep and rising, meaning the rate of change is 1 centimeter per second. Alright, so I think that'll work out. What's the deal? So I want to do the area of a circle, it looks like. So because that puddle, you know, the surface of this puddle of fudge is pi r squared. Alright, so normally I would just blaze right into taking a derivative of this thing, except there's a little situation going on here, which is I have r's in this. So if I take the derivative of this pi r squared thing, I'm going to get an r and a dr dt. But the givens were both h's. I had an h and a dh dt. So don't I wish that instead of r's in this formula, I had h's? But obviously, radius is what you need. That's part of the circle. This h has nothing to do with the circle. Or does it? If I zoom in, because remember, we haven't used this 30, 60, 90 thing yet on this problem. And that was kind of like it was sort of screaming out to us to use it. And we also haven't used the fact that it had 60 degrees at the bottom, which is another tip off. There was given information we haven't used yet, so maybe that's helpful. If this is h and this is r, but I'm in a 30, 60, doesn't that mean I know the ratio between r and h? H is just going to equal r times the square root of 3. So that means if I divide both sides by square root of 3, I get r equals h over root 3. And now all of a sudden, I've got something I can plug in for r in this formula right here. So I'll just take that, plug it in right there. So I'll get a equals pi times h over root 3 squared. Now you notice I did not rationalize the root 3. I didn't turn into like h root 3 over 3. And that's just because I was in the middle of a problem. That rationalizing stuff is just something you do at the very end when you're about to circle your answer. But anytime you're in the middle of a problem, you don't want to rationalize because it makes for more work and more messiness. And sometimes it goes away. And this is actually one of those cases where if I just square out that what's in the parentheses there, I get h squared over 3. So the square root got squared away. Excellent. So now I can take the derivative with respect to t, and I got myself dA dt, which is what they were asking for, equals pi, oops, oh no, I haven't done it yet, sorry, 2h, for a second there I thought I forgot my dH dt, but then I realized, wait a minute, I'm not even to that point in the problem yet, all over 3. So that works, we can plug stuff in. So that's 2 pi times h, which is 5, times dH dt, which is 1, all over 3. Dun, 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 dun. So we got 10 pi over 3. Alright, so we won't even bother plugging that into a calculator because it's already a nice, round looking kind of trigonometric number. And then what do we want to know? Hey, what are the units? So that's going to be, looks like our units here are centimeters per second, but since it's the rate of change of area, it must be square centimeters per second. Alright, cool beans. Alright, last one, we got a sundial. Let's see what's up with this. So a sundial, they stuck a metal triangle into the ground so the 30-degree angle is sticking up. Alright, so first things first, we got 30, 60, 90 sticking up into the ground, in the air. Alright. The hypotenuse of the dial is 2 meters. So that's a 2 right there, which means this is a 1 and this is a root 3, hypothetically. Not sure if we'll need that or not. How fast is the hypotenuse of the shadow growing? Whoa, so the shadow. We don't know how big the shadow is, right? If it was close to noontime, it'd be a really small shadow. If it was late in the evening, the shadow could be enormous. So we're not sure about the angles or anything on that. If the hypotenuse of the dial is 2 meters, how fast is the hypotenuse of the shadow changing? So let's just call that c, because like the Pythagorean theorem has a c in it. So dc dt. We're wondering how fast is that growing? If the area of the shadow is changing at 0.1 meters squared per minute. All right, so they gave us the rate of change of area, they asked for the rate of change of the hypotenuse of the shadow, and they told us, so that like that when thing they always say, like when something equals something, they said when the angle of the sun is 45 degrees, but that's super weird, right? Because we're talking about a 30, 60, 90 triangle. What does 45 degrees have to do with anything? Well, it turns out that actually tells us the length of the shadow. And it tells us that the length of the shadow is actually the same as the height of the sundial. Because at 45 degrees, if you got something sticking up like this, making a shadow, or you got this sticking up, the calculator sticking up, making a shadow. I don't know if you can see that against me. So then, and then the shadow, if the sun's coming in at 45 degrees, it's going to hit and form a 45, 45, 90 triangle. So if here's my sundial, here's the sun coming in at 45 degrees. That means I have a 45 degree angle here, 45 with the ground. And that means that the height of the sundial is going to be the same as the length of the shadow. So what that tells us is that our shadow at this moment of 45 degrees, our shadow is congruent to our original triangle. So they're basically telling us that C equals 2 at this moment. And the base is of course going to be 1 because that's always the same. And then the height will actually be, or this thing right here will also be root 3 at the time. Don't know if we're going to need that or not. We'll see what happens. Alright, so they've asked us for dc dt. Alright, so and they gave us the rate of change of area, which means we're using the area of a triangle. So area equals 1/2 times base times height. And on this one, the base is always 1. That's not changing, that's not a variable, it's just constant. So in this case, area actually just equals 1/2 h. Alright, so that's interesting. If I took the derivative right now, I would have a dA dt and dH dt. dA dt I have. What about dC dt though? Because what I want is dC dt, but this has an h in it instead of a c. So if I took the derivative right now, I get a dH dt instead of a dC dt. Bummer. Well, maybe we can use one of those secondary deals. Because isn't there a ratio between h and c because it's a 30-60? So if the hypotenuse is c, doesn't that mean that this side is square root of 3/2 times c? Because if this is c, this side right here is c/2. Then you multiply that by root 3 to get up to here. So we can rewrite this as a equals 1/2 times root 3/2 times c. Alright, I think that worked. So I'll just rewrite that up here a little bit. So a equals root 3/4 times c. Alright, so now I've got something I can take the derivative of pretty easy. I'll get dA dt equals square root of 3/4 times c, derivative of c, which is dc dt, which equals square root of 3/4 times dc dt is one of the, oh, that's what we want actually. Alright, so we want this. So we want to isolate this. We'll have to multiply both sides by 4/root 3 in order to cancel this out. So we get that dc over dt equals 4/root 3 times dA dt. And then of course dA dt they told me is 0.1. So I can just plug that in. I get 0.4/root 3, which is 0.23. And then all we have to do is just figure out the units. What are they? Let's see, we're asking for the rate of change of a hypotenuse, so that's a length. And what were all my units were in? Looks like we had meters. So that's meters per, and then what's my unit of time? Seconds? Oops, minutes in this one. So the answer is 0.23 meters per minute. Alright, so now those were pretty sketchy. Hopefully what you noticed there was because these problems were more difficult, there was always a secondary thing we were doing. Just like in all the easier related rates problems, we had to have one big formula we were going to take the derivative of. It was like either take the derivative of the area or the volume, pi r squared, the area of a triangle, whatever. You just needed a formula that you were going to take the derivative of. But then what happened in all these problems was that we realized, hey, wait a minute. This formula has r's in it, but I want h's. Or it's got h's in it, but I want c's. So then once we had that main formula, before we took the derivative, we wanted to use substitution and sort of the geometry of each individual problem to replace one variable with the variable that they had asked for or that they gave us. So that's just a trick, and that's what makes harder related rates problems harder, is a lot of times the way they get harder is you'll have the original formula you want to take the derivative of, but then you'll have some other geometrical relationship that forces you to sort of substitute in one letter for another in order to make all the derivatives be the letters you actually want them to be. So that's the thing that takes a lot of practice. But once you get in the habit of realizing, oh, there's always going to be two equations, the main formula and then the geometrical ratio or whatever, and just at that point it just becomes plug and chug yet again, which is what we like, right? Thinking is the enemy on a test. So the closer you can get to plug and chug by practicing and all that, the better you'll do.